All right, on to the second part for today. We're going to go over the last 25 questions of the 2019 multiple choice practice test. We did the first 25 in a previous video. We're going to finish it up here. So first we have another set of 3 questions. The structure of haloacetic acids, this thing, okay, where X can be an F or a Cl or B or an I. This is not something we really deal with very often, but we'll see if we can answer the questions about it. The information in the table, it gives us the 4 acids, their pKa's, their Ka's, and their molar mass. So what we're going to need as we go through the question, remember pKa is kind of like pH, right? The p is the negative log, and basically the smaller this number is, the stronger the acid. So all of these, this is going to be the strongest acid. Now the other way to look at that is with Ka. The bigger the Ka is, the stronger the acid is. You'll see that that also matches. This is the biggest number of these. So fluoroacetic acid of these 4 is the strongest acid. You can look at either of those to figure it out. And it is the smallest. And then iodoacetic acid has the highest pKa, so it's the least acidic. Or you can look at the Ka, it's the lowest, so it's least acidic. All right. 26 says, which compound, and it's looking at chloroacetic acid, or iodoacetic acid, right, has the lower boiling point. So which one is easier to boil? Okay. Essentially, most of the structure is going to stay the same, so we don't really have to consider all of this. They'll all have this hydrogen bonded stuff, but the X here is swapping out. Chloroacetic acid will have a chlorine here, and iodoacetic acid will have an iodine, and that'll change the mass significantly. Iodoacetic acid is much larger, and the bigger a molecule is, generally, the more London dispersion forces it has. And that's what will cause it to have a higher boiling point. So chloroacetic acid will have the lower boiling point because it is smaller. And our answer choice that matches that is A. Chloroacetic acid, because the London dispersion forces among its molecules are weaker. All right, 27. An aqueous solution contains small but equal concentrations of chloroacetic acid and fluoro. So we're looking at the top 2 this time. Okay. Which statement comparing the percent ionizations of the 2 acids is true? So the percent ionization of an acid is just how much of it turns into products. So if you have an acid, it will want to dissociate, split into H plus and A minus. And basically, the stronger an acid is, the more of it it's going to split apart. Remember that strong acids split 100%, but the stronger you are, the higher your percent ionization will be. So we're just trying to pick the stronger acid between those 2. And like we said, fluoroacetic is the stronger of the 2 acids. So its percent ionization will be the highest, which is answer choice B. It says it backwards here, but the percent ionization of chloroacetic acid is less because fluoroacetic acid is the stronger acid. But then we get into 28. A student titrates 10 milliliter samples of 1 molar solutions of each of these acids with a standard solution of NaOH. So a long sentence to say, I'm going to add a little bit of NaOH to each of these samples, and everything's like even. All right, which of the following statements correctly predicts the volume of NaOH needed to reach the equivalence point? So this is kind of a trick. You might want to think that, like, okay, down here, iodic is the weakest of these acids, so it would need the least amount of base to neutralize it. But that is not true. The strength of an acid does not matter when you're neutralizing. It's just how much of it you have, right? A strong acid and a weak acid, if you have 5 moles of both of them, will both need 5 moles of base to neutralize. The strength doesn't matter during an acid-base neutralization. So that means actually all of these acids are the same. They need the same volume of NaOH to reach that equivalence point. 29. The value of Kw. Kw is the special dissociation for water. Here is the formula sheet. It does have Kw on here as well. It tells you Kw, if you're not sure which one that is. That is just H plus times OH minus. And this is its value at 25. And that's why if we take the negative log of this, we end up with a pH scale up to 14. But at different temperatures, that scale is not the same. So at 40 degrees, it's not going to be 1 times 10 to the negative 14th. Instead, we have our Kw is H plus times OH minus are water dissociating into its acid and base parts. That equals 3 times 10 to the negative 14th. Well, when an water molecule splits apart, it'll always split as a 1-to-1 mole ratio. It always makes exactly 1 H plus and 1 OH minus, which means the concentration of these guys is always going to be the same. So another way to say H plus times OH minus is just to say H plus times H plus, or H plus squared, right? Because these numbers are the same anyways. All right, now just to find H plus, I'm going to take the square root of that. So let's do the square roots of 3 times 10 to the negative 14th. I get 0.0000173, but I need the pH, so I'm just going to take the negative log of that answer. 6.76, which rounds to 6.8. The little shortcut you can do anytime you have this sort of problem, it'll usually be the same thing, is you can show the work if you want, or you could just take the square roots of the Ka and then just do the negative log to make it the pH. Like, that's essentially the math we did. So you don't need the justification here, but that's essentially what you'll do. Number 30, a 1 mole sample of helium at 25 Celsius is mixed with a 1 mole sample of xenon at 50 Celsius. So I'm mixing these two gases together at different temperatures. Let's see what that's going to make us do. It says, which of the following correctly predicts the change in kinetic energy and average speed of the xenon atoms that occur in the mixture as it approaches thermal equilibrium? Just a little fuzzy there. Okay, so basically, thermal equilibrium means things are reaching the same temperature. Looking at the xenon atom specifically, which started at 50. As these two things mix together, they'll eventually reach an average temperature somewhere in between. Maybe it'll be 30 or 40, but xenon's temperature will go down. As the temperature of the xenon particles decreases, their average speed will also decrease. Right? Because the temperature gets lower, things slow down. Well, if the speed is decreasing, let's look at the kinetic energy. The kinetic energy is 1/2 mv squared, and v is speed. So since the speed went down, kinetic energy also will go down. 30 is d. Okay. Which of the following best helps to explain why NaS is more reactive with water than MgS? All right, so both these things are very reactive with water. Sodium has a configuration of, well, I'm just going to write the end. It ends with 3s1. It has 1 valence electron, basically, whereas magnesium has 2. And that's why sodium makes a plus charge and magnesium makes a 2 plus charge, because when they react, they're generally going to try to react to lose 1 or lose 2 electrons, respectively. Well, sodium only needs to lose 1 electron to satisfy the octet rule. It is super close. Because of that, it actually is easier to remove that electron. Magnesium also wants to lose its electrons, but since it has to lose 2 full electrons, it is going to take a considerable amount more energy. Right? Na is so close that it really wants to lose that electron. And how we're going to say that is D. The first ionization energy of Na is less than that of Mg. Ionization energy is the energy to lose an electron. Sodium really wants to lose an electron, so it has a very low ionization energy. Number 32. At 25 Celsius, enough distilled water is added to a 30 milliliter sample of nitric acid, with a pH of 4.2. So I have a 30 milliliter sample of nitric acid with a pH of that. And I'm going to add some water to it so that the final pH is 5.2. Right. So I basically have my beaker and I have 30 mLs of some acid. And the acid's pH starts at 4.2. And I'm just going to add in some amount of water. Oops, let me write that in the right spot. Some amounts of water until the pH becomes 1 point higher. So the first thing we need is kind of the definition of pH. Because it's a logarithmic scale, increasing the pH by 1 is actually making it 10 times weaker. Right? Every change in one pH point, 4.2 to 5.2, is making it in this direction 10 times weaker, which means you are diluting it to be 10 times weaker with the volume. So if you started with 30 milliliters, you're going to dilute it until you have 300 milliliters. Right? 300 milliliters of the same acid would go up by 1 pH point. Okay? But it's asking how much water do you need to add? I need a total volume of 300. I already have 30, so I need to add 270. All right, I do think the questions kind of get harder as you go. I think the first part's easier. Some of these are pretty tricky, and 33 is one that's definitely one they ask a lot, but it is kind of tricky, this idea. Student observes that the equilibrium constant for a reaction is greater than 1. So let's stop there for now. What does that mean? That means K is greater than 1, which means this is a product-favored reaction. Other ways to say this is delta G is negative. Or if you want to get like the very last chapter, we say E, the cell potential is positive. All of these are different ways to say the reaction is spontaneous. It is thermodynamically favorable and will go to the right. Okay, so this reaction will go to the right when it's below 500 K. So if the temperature is kind of cold, relatively, the reaction is favorable. But it is less than 1.0, talking about the K. It is not favorable, basically, when it is hot. So here we have a reaction that delta G is negative when it is cold. So it is spontaneous when it's cold, but delta G is not spontaneous when it's hot. And what we need to look for is the combination of H's and S's that make that statement true. Now our formula, delta G equals delta H minus T delta S. Let's start with the positive part. To make G positive, but only when it's hot, right? When it's hot, that would mean we have to look at kind of temperature here. That when it's really hot, that means this term is going to be the more important one. It's going to overweigh whatever H happens to be. So we need to find a way to make this positive only when this number is really, really big. I'm subtracting this number, so in that case, S would have to be a negative number. S has to be negative because when you subtract a negative, you're adding, and we need our final answer to be a positive. When the temperature is really hot, the positive numbers here is going to override whatever H is regardless. So I know S is negative, or less than 0. All right, now kind of the other part is I can look at when it's really cold. When it's cold, temperature is going to be a much smaller number. So when it's really, really cold, this number won't be important. Only the H will be important. Okay, so it says when it's cold, G will be negative. Well, if basically I have all of that gone, for G to be negative, H also has to be negative. So H is also negative. So D is the right answer. Both H and S have to be a negative number for both of those statements to be true. But it's definitely a tricky sort of math puzzle question. All right, 34. A saturated solution of CuSO4. So first of all, I'm going to break it down again. Saturated solution means you have as much CuSO4 dissolved in here as possible. No more of this is going to dissolve unless you add some more water. You have the maximum amount of CuSO4 in your water. Okay, so it's shown above. It's left on an uncovered lab bench at a constant temperature, so some of the water starts to evaporate. So over time, the water level will go down as the water evaporates. Now the water is just going to be literally H2O leaving. The CuSO4 crystals, the CuSO4 in the solution, that can't leave. We're basically just getting rid of some of the water. So as the solution evaporates, 1 milliliter samples of the solution are removed every couple of days. So they took a sample of the CuSO4 on day 1, and then they waited for some of the water to evaporate and took another sample, and then waited a few days, took another sample, and they're trying to measure how much SO4 is in that sample. But it's observed that the amount of SO4 in the solution doesn't change, even though your solution is losing volume, the concentration is staying the same. And all of this comes back down to the idea of saturation, right? As I lose water, some of the sulfate ions that are in solution, they have a maximum amount that can be in there. So as you remove water, some of these actually turn back into crystals, and the amount of CuSO4 crystal would actually increase. And as you keep removing water, the amount of SO4 in the solution stays constant because any extra SO4 has to turn back into crystals because you already have the max amount of CuSO4 in this water. So what you would expect to see is all of those samples are the exact same. And the way to explain that is D. As the water evaporates, more CuSO4 is being made because that SO4 has to go somewhere. It turns back into CuSO4. All right, for 35 here through 38, we have an experiment. And it is an experiment with eggshells, kind of like the one we did, but this one actually has an extra step compared to that. So an experiment is performed to measure the mass percent of CaCO3 in eggshells. That's exactly what our experiment tried to do, was figure out how much CaCO3 was in an eggshell. So an eggshell has some of this chemical in it, but there's also plenty of other things. On average, an eggshell might be between 60 and 90% calcium carbonate. Okay. So what they did was they took 5 different samples of just CaCO3. So they're not talking about eggshells, they're just talking about this chemical. This is separate. So they took some CaCO3 of a known mass and reacted it with hydrochloric acid in some containers. And that produced a little bit of gas. The pressure of that gas was recorded and charted on this graph here. So I took 5, these dots represent my amounts. I took like this 0.07 gram sample of CaCO3, reacted it with some acid, and recorded how much gas was produced and marked that over here. And I repeated that, but with 5 separate samples. And you'll notice they're pretty linear. The amount of CaCO3 you start with directly corresponds to how much gas is produced. This is making a standard curve. So nothing's really been done with eggshells yet, but this is kind of a relationship. It tells you if you know how much gas is produced, you can kind of figure out how much CaCO3 you must have started with. So if you do an experiment with eggshells now where you don't know how much CaCO3 you have, and it produces, for example, 0.09 ATMs worth of gas, you can figure out there probably was about this much-ish CaCO3 in that sample. So this is creating a standard curve, like we did with the Beer's Law lab, and might do with some other labs at some point. This is an example of that. And then they kind of did their eggshell thing. They took an eggshell sample and reacted it with some hydrochloric acid. Their eggshell sample started at 0.2 grams, and they recorded the pressure in this container before and after the reaction. So the difference here will be what's important. So when you subtract these two numbers, you end with 0.07 ATMs. This is how much gas was made when we actually did the experiment. We took some eggshell, we reacted it all with hydrochloric acid, and it produced this much gas. What that allows us to do is go to this chart and kind of estimate about 0.14 grams of calcium carbonate must have been in that sample. So this is how big my entire eggshell sample was, and I was able to figure out, because of how much gas was produced, that that eggshell sample had about this much of the calcium carbonate, because the calcium carbonate is the stuff making the gas, right? And this will come up later. Usually you want to find the percent of calcium carbonate. So you would just do the weight of the calcium carbonate divided by the total weight of the eggshell times 100, and that would give you a percentage. So this one would be around 70%. But that's not even really looking at the question yet. That's kind of getting ahead of myself, explaining what the purpose of this lab is. Okay. So my first thing here is asking, which of the following equations represents the species that react and the species that are produced when those things are combined? So we're looking at our different problems here. We're taking some HCl, or just H+, reacting it with CaCO3. Okay. This reaction's a little bit tricky, but hopefully it's kind of similar to a couple we've done this year. When you take carbonates and you react them, here's another example of a reaction we did this year. We took some sodium hydrogen carbonate, which is baking soda, and we heated it up and it decomposes. The Na plus kind of does its own thing. Actually, no, it doesn't. I lied. The Na forms with the carbonates. Mine's blanking there. The Na and the carbonate form together, and your other two products are H2O and CO2. Right, this is baking soda. When you heat it, it makes some sodium carbonate, and it makes some water and some CO2. That's the only reaction we've seen that's kind of like this. The answer to this one's B. Those are the two products that you're looking for there. I don't have a great other way besides that I just kind of recognize when you break apart carbonates, they make water and CO2. So like that's kind of what I would try to remember. Anytime you have a carbonate or a hydrogen carbonate or a calcium carbonate, that's usually the products you're going to make when you mix it with an acid or when it decomposes. But don't get that one, that's not a big deal. All right. So the mass percent of the CaCO3 in the eggshell, that's kind of what we're doing. Now I got 70%, but I could have estimated this slightly wrong. It looks like maybe this is above 0.14 a little bit. 70% though is my estimate. That's closest to 75, which is the answer. All right. I would have preferred if it was a little bit closer to 70, but that is fine. Another sample of eggshell reacts completely with 4 milliliters of HCl solution in an unknown concentration. If the reaction produces 0.095 atms of gas, the concentration of HCl was what? So this is kind of a backwards way to think about it. So we're going to start with the reaction produced this much gas. I'm going to go back to my chart. 0.095 moles of gas would be here. Right? And I'm going to estimate that would give you pretty much exactly 0.20 grams of calcium carbonate. So that's kind of the first thing I want to look at, right? If the reaction produced this much gas, that equals about 20 grams, 0.20 grams of calcium carbonate. Okay, so the first part is you have to react that with HCl until all of this reacts. Well, this is my volume of HCl, and I'm looking for the molarity. But I can't really find that now, but molarity is moles per liters. I'm looking for the molarity that gave me milliliters. If I can find moles of HCl that I need, I can plug into this formula and get my answer. I know I used 0.20 grams of CaCO3, so if I convert that into moles of HCl needed, then I'd be able to plug that into this equation to find molarity. It's a weird backwards way, like a train track stoichiometry problem. Okay. So I'm going to convert this grams of CaCO3 on the bottom to moles of CaCO3. All right, this one, usually they give you the molar mass, but they didn't on this one, so I'm going to have to add all that up together. CaCO3 is about 40 plus 12 plus 3 times 16. Oh, about exactly 100. Weird. All right, that's moles of CaCO3. Now I'm just going to turn that into moles of HCl. And I need my mole to mole ratio for my reaction up here. So CaCO3's number is a 1. HCl's number is a 2. It's not super fair because if you didn't have this one, you probably wouldn't be able to get this one. But if you do look, every answer choice has that same ratio. So that's kind of a way they could expect you to figure it out. So then I have 0.2 times 2 divided by 100 equals 0.004 moles. Divide by 4 milliliters is 0.004 liters. I have a 1 molar solution. Answer choice D. So these problems are getting definitely more complex kind of as we go here. 38. Which of the following modifications will increase the rate of the reaction the most? So I want to speed up my eggshell reaction with hydrochloric acid. So we can kind of think back to our lab we did with reaction rates with our Alka-Seltzer tablets. We want to speed up how fast they dissolve. And a couple of ways to do that. You can make it super hot. You could stir it really fast, or you could crush it up super, super fine so that there's much more surface area. And that's the answer here is D. Using eggshells that are more finely powdered will speed up that reaction significantly. Okay, so those are always some hard questions there when you have those experiments to look at. Unfortunately, that's one we did, but that was a little bit different than our version of it. Samples of NaF solid, so ionic salt, NH4Cl solid, another salt, are dissolved in separate beakers that contain water. One of the salts produces a slightly acidic solution. So when one of these things dissolves in water, it makes it a little bit acidic. Which of the following equations represents the formation of that acidic solution? This is something, honestly, we brushed over a little bit. We have neutral salts, like NaCl, that are completely neutral. If you dissolve regular salt in water, the pH will not change. But sometimes things will change a little bit. And these are two examples of those kinds of salts. So first, I'll talk about how you know, and then I'll talk about how you could get the answer maybe without knowing. Okay, so NaF and NH4Cl. Here is not the most scientific way to figure it out. It's not looking at all the chemistry exactly, but this is a trick that always works. If you want to find out if a base is acidic or basic, right, first you're going to look at the metal, Na. Where does Na come from? If we're talking about acids and bases, the most common thing with Na would be like an NaOH. That's a strong base. So Na is strong. It comes from a strong base. F comes from HF. That's the common acid we'll see with F in it. Right? HF is a weak acid though, so it's weak. So this salt is made of a strong base component and a weak acid component, and the base is the strong part, so this will make a slightly basic solution. Now, to be clear, that's not why, but that is a good trick to kind of remember it. So when this salt, NaF, is dissolved in water, it becomes a little bit basic. The opposite will be true for over here. I have NH4 that comes from NH3, which is weak. Cl, of course, comes from HCl, which is strong. The acid component is stronger this time, so this will make a slightly acidic solution. NH4Cl. So I'm looking for the reaction that has NH4 in it, which is C. The other way you might be able to kind of get at this answer is you're making a slightly acidic solution. So we're just going to look at the products. Which of these products have acids? Remember, an acidic solution just means it has H pluses or H3O pluses. So I can eliminate B and D just because those are basic solutions. They make OH minus. So even if I had no idea, I could kind of use those last couple words there to guess between A and C. But this time the answer is C. Not the biggest deal though. All right, here I have a reaction. Carbon in diamond form turns into carbon in graphite form. And this is a delta G that is negative. That means it's spontaneous, which means this reaction is thermodynamically favorable and should happen. Okay, but if you have a diamond ring, you know that your diamond ring doesn't just decompose into graphite, into pencil lead, right? So that doesn't actually happen. This is we'll kind of talk about why. Which of the following best explains why the reaction represented above is not observed to occur at room temperature. This is thermodynamically favorable, but all that basically means is the free energy that you're starting with of the diamond is actually higher than the free energy you end with. This would be the graphites. Right? It just goes down. Right? So this is kind of what a spontaneous process is. When you consider the heat and the entropy, it goes down. Spontaneous reactions do that. Your paper that I'm writing on here is its spontaneous reaction to turn into carbon dioxide and water and other things like that. But it doesn't happen because of activation energy. Right? The reaction can happen, but only if you overcome that activation energy. Like this paper, I would need to spark it somehow. That amount of energy I'm adding to it would make the whole thing burn. but that activation energy is stopping a spontaneous reaction from occurring. Spontaneous doesn't mean that it will happen naturally. That just means that it should according to the energy. Thermodynamic quantities are what they call state functions. They don't actually look at the pathway of how you get to the end product. It just says, oh, I end with slightly less energy, so this reaction should happen. But it can't consider things like the rate of the reaction or the activation energy required there. So the right answer here is actually C. That's that word activation energy. The reaction has an extremely large activation energy. It takes a lot of energy to start breaking apart the diamonds due to their three-dimensional bonding. 41. The reaction represented above occurs when some amount of this acid is completely dissolved in water in a flask and titrated to the equivalence point. So that's a lot of words, but I'm just taking a little bit of this and adding some NaOH until I get to the equivalence point. So that means however much of this I'm starting with, I'm using an equal amount of NaOH. At the equivalence point, all of my acid and base have been used up, and I'm left with no acid or base on the left side. But I am making products, so I will make some of these things as the reaction proceeds. This thing here would be our conjugate base. Okay, so which of the following statements is true? And we are comparing the C9H8O4 to the C9H7O4 minus. Which one will it be more of? Since we're at the equivalence point, all of this is used. There's actually zero of this left because the NaOH and this are reacted completely to equivalence. And I don't know exactly how much of this there is, but they'll be greater than zero. I made a little bit of this as I proceeded, which is why my answer is B. My C9H8OH is less than my amount of my product version of it. At the half equivalence point, they would be equal, but at the full equivalence point, there's none of this left and only this left. All right, another three-part question here. We have some sort of super fancy looking molecule up here at the top. The structural formula for the glycinium cation is shown above. Arrows indicate the pKa values of the labile protons in the molecule. I don't even know what that means. All right. So we have our H pluses here with their different pKa's. It doesn't even, I don't think, really going to come up in the question. But what's the approximate bond angle in the glycinium cation between HO and C? So my HO and C are these three here. So what you're going to do to figure out their bond angle is go to the middle atom. I know it's super tempting to just say it's 180 because that's how we draw it, but our drawing is a simplified version. Go to the center of your bond and figure out its bond angle by looking at the number of bonds it makes. It has 2 bonds. And the number of lone pairs it has, 2 lone pairs. 2 and 2 makes a bent structure. If I wanted to zoom in on it, it would look like one of these guys. And these lone pairs are going to push in on these bonds. So this has a basic shape of a tetrahedral, which would be 109.5. But the lone pairs squish it a little bit, so it's going to be just less than 109.5. Answer is C. So there's a lot of trick there. It can be hard to determine the bond angle inside of a structure, especially when it's not drawn three-dimensionally. That's kind of the problem with this. So any of these things that make 4 bonds with no lone pairs, these angles and stuff are actually 109.5 because they're not showing you the three-dimensional structure here. Now this carbon here, for example, its bond angles aren't because it only has 3 electron groups. Its bond angles would actually be 120, which it doesn't look like that's true as well based on the picture. So the picture can be misleading in a couple of different ways. So to figure out the bond angle of a specific bond, just look at that center atom, how many things are attached to it, what would that make its bond angles? What is true about the geometry in this cation? So which of these statements is true? This one says the leftmost C atom and all the atoms directly bonded to it are in the same plane. So a little stuff about being in the same plane. If you have, I'm just going to go down here for a sec. Something like this. This is a linear shape. This is 2-dimensional. The idea is these electron pairs, right, these bonded angles here, want to get as far away from each other as possible. The x's want to escape each other. This is as far away as they can get from each other is 180 degrees. Even if I use 3 dimensions, I can't rotate this x in any way to get it further away from this x. And that is the whole idea of VSEPR, the valence shell electron pair repulsion, is your x's want to get as far away from each other as possible. If you have 3 x's, what's the furthest away they can get from each other? Well, with 3 x's, they actually are 120 degrees as well. Even if one of these x's, say my pencil is this top x, wants to get further away from both these x's, it can't. Even if it rotates up or rotates down into the page or something, it can't get further away than 120 degrees mathematically. And that's why both of these shapes are flat. They are a single plane because that is the furthest those x's can get away from each other. But anything with more than 3 electron pairs, 4 for example, even though we draw it like this, those x's look like they'd be 90 degrees. They are not, because in 3 dimensions, these x's can get further from each other if they make a tetrahedral shape. So they'll make a shape that looks something like this. And it's kind of hard to imagine because the 3D doesn't really work very well, but the bond angle is actually 109.5 between all of the XX bonds, right? So this would be like, basically imagine like a tripod camera, right? With 3 legs that are equally spread from each other, and then the camera is coming straight up, right? And that's as far as away those X's can get because they're using the extra 3-dimensional space. And that's what makes things confusing. 2 or 3 electron pairs will keep you flat in the same plane. 4 or more, and you'll go 3-dimensional to get further away from each other. So when we go back to 43 then, the leftmost C atom and all the atoms directly bonded to it are in the same plane. This C it's talking about, that is not true. They're not in the same plane because there are 4 bonds there. They're going to have a 3-dimensional shape. Answer choice B says both C atoms and both O atoms. So we're talking about both C and both O. All 4 of these atoms are in the same plane. So to figure that out, I go to the middle atom. It has 1, 2, 3 bonds. Even though there's other bonds changing things, these 4, because they make a trigonal planar shape, are in the same plane. B is the answer. That's tricky. 44. Which of the following statements is true about this sodium glycinate as represented above? So you have all of this ion, which is negative, and an Na+. You have a positive negative charge sort of thing going on here. It is an ionic solid at room temperature. That kind of makes sense because you have a positive and a negative charge. It is not soluble in water. This seems like it would be because you have a positive Na and a negative thing here. Na usually makes things soluble in water. It evaporates easily because of the lack of hydrogen bonding. It does have hydrogen bonds. It has NH bonds. Even though it lost the O, it still has NH bonds, so that's not true. It dissolves in water to form an acidic solution. I don't see any H's or OH's or anything, so that's probably not true as well. But 44 is A. It is an ionic solid. When it dissolves, it splits into its ions, even though its ions are super weird. All right, solid carbon tetrachloride, CCl4, is represented by the diagram above. So each of these little shapes is its own CCl4. So it looks like you have 8 total of these molecules, kind of making like a little cube. But all of these molecules are attracted to each other through whatever this dashed line represents. And that's what we're looking for. The attraction between the CCl4 molecules that hold the molecules together in the solid state. So I'm not talking about this bond. That's an intermolecular, That is an intramolecular force that's holding a single molecule to itself. That's not what it's asking about. It's asking about these dashed lines. Why do these molecules stay next to each other? Those are intermolecular forces doing that. So it's not a covalent bond of any kind. It's some sort of intermolecular force. So what I need to figure out is, does that come from temporary dipoles? That's a fancy way to say London dispersion forces, or from permanent dipoles, from regular dipole-dipole forces. So then I have to look at my CCl4 molecule. Okay, and that's going to be a nice symmetric molecule if we draw it in 2D or if we draw it in 3D. So even though an individual bond is polar, all of those intermolecular force, all of those dipole moments will cancel, and you end up with a non-polar molecule. So the answer is C. 46. Which of the following is a list of the minimum amount of data needed for determining the molar enthalpy of the solution of KCl, solid, and pure H2O? Make a bunch of assumptions. Let's skip over all that. That doesn't matter. This is when you're getting to the end of the test, and they are really cooking with the crazy questions at this point. All right, so basically what this means is I want to take some KCl, put it in water, and see how its temperature changes, basically, to check its enthalpy of solution, basically meaning how much heat is produced when it dissolves. So usually when we're adding things to water to do temperature change, we're going to use Q equals MCAT. If I want to see how adding this solid affects the overall temperature, I can do MCAT equals MCAT. The MCAT of the solid and the MCAT of the water will equal each other because the amount of heat lost by one thing is gained by the other. And this is all the info I need. I need the mass of the solid and I need the mass of the water. I need the specific heats of both, okay, which it tells you the same specific heat capacity as pure water. So that's what that's for. And then you need the change in temperature. So you need the final and the initial temperatures of the final temperature of the solution and the initial temperature of both. Our answer here that has all that information is C. All right, I'm not going to spend a lot of time breaking that down because they're not going to ask an exact question like that. That one, they're cooking with these questions. All right, my reaction here, X2, Y2, equilibrium with some X, Y. The K is about 3. So that means it's a slightly product favor, you're making some XY. A mixture of these 3 gases is placed in a previously evacuated rigid container and allowed to reach equilibrium. So I take all 3 of these gases, shove them in a container. Okay. Which of the following sets of conditions would lead to the formation of more product as the system moves to the right? So I want to add this initial amount of stuff, and I want the reaction to go to the right. For here, the formal way to do it is to look at K and Q. If K is bigger than Q, the reaction will go to the right. If K is less than Q, the reaction will go to the left. K is given to us up here. We need to find Q. Remember, Q is products over reactants just like K. So this would be my XY squared over X Y2. I'm just going to plug in my initial conditions in here until I get a Q that is smaller than K. And the one that does that is actually A. I'm not going to go through all the math for all 4 of them, but I will do it for A. So I'm going to plug in 0.2 squared over 0.4 times 0.4, which would be a relatively small number, 0.25. 0.25 and 3 is greater, K is greater than Q, so the reaction makes more products. But how I knew this before I even did the math, though, was just kind of playing which of these things is not like the other. In A, compared to product to reactants, you have a lot more reactants. If you have more reactants, it kind of makes sense that it might go to the right. Down here in B, your products is greater than your reactants. C, products greater than your reactants. D, products greater than your reactants. All 3 of these follow the same trend. They can't all be right, so they're probably all wrong. And the one unique one that has more reactants and less products is probably the one that's right. but you could do this math for all of them to find that out as well. All right, the structural formulas of two isomers are above. So it doesn't matter, isomers are things with the same elements and different shapes, but that doesn't really matter. Which of the two liquids has a higher vapor pressure? So we're looking at vapor pressure, we need to look at IMFs. Let's compare the IMFs of these two seemingly very similar molecules. They have the same stuff, it's just in different places. So if I'm looking at IMFs, their LDFs are exactly the same because they have the same exact molar mass. That's mostly true. We'll go with that being true. Okay. But what's really different here is their polarity. Let's take a look at the trans isomer here. They call it trans because these are on opposite sides. CLs are on opposite sides of this double bond. This one is slightly polar and has a dipole moment this way, but there's also a dipole moment this way. But those are in exact opposite directions. They cancel each other out. This molecule is non-polar. Compared to the cis isomer, cis means same, right? You have these molecules are on the same side. So these don't cancel out. You have an overall dipole pointing up. So this is polar. This one has higher IMFs. So the cis isomer has higher IMFs, which means it has lower vapor pressure. Remember, having a high IMF will give you a higher melting point, a higher boiling point, but the one that's different is vapor pressure. Vapor pressure is basically how much vapor your solution makes. So imagine a closed container with a solution, and some of this liquid will turn into gas. The very fastest of those molecules will turn into gas. And the amount of gas you have is your vapor pressure. But if this solution has very high IMFs, these molecules need to be moving extraordinarily fast to be able to leave the liquid phase. The forces holding them as a liquid is stronger. So things with high IMFs actually have a lower vapor pressure because a lot of the gases can't escape. If you have a gas with a relatively low IMF, it's a lot easier for those gases to leave. And you might end up with a whole bunch more molecules in the gas form and a much higher vapor pressure. All right, our answer here for 48 is D. Which one has higher vapor pressure? The trans isomer has a higher vapor pressure because it's not polar. It has only London dispersion forces, so it has lower IMFs, so it has a higher vapor pressure. 49. All right. The concentration of F- in drinking water that is considered ideal for promoting dental health is this. So this is how much F- should be in your water. Based on this information above, the max amount of Ca2+ that can be present without lowering this F- below the ideal level is closest to what? This feels weird. Okay. So my KSP basically is a measure of how much stuff dissolves. KSP is equal to Ca2+ F- squared. Products over reactants, except we don't include the solid. Right? And essentially the idea is we need to kind of solve this formula to see how much Ca+ I'm allowed to have, basically. All right. So let's go ahead and just plug everything in. We have 4 times 10 to the negative 11th. I have my amount of calcium that I need to find, the maximum amount, if F is equal to 4 times 10 to the minus 5 squared. So I'm going to do my 4EE negative 11 divide by 4EE negative 5 quantity squared. 0.025 is how much calcium I'm allowed to have. Kind of a weird question, but KSP will always kind of be the same formula. So if you're given 2 of the values, you can find the last one. All right. I have a couple of reactions with some Ks over here. The formation of Fe and O2 from FeO is not thermodynamically favorable. Okay, so this reaction at the top is not favorable at room temperature, which adds up to me because K is less than 1, which means G should be positive. So this reaction doesn't work at room temperatures. That makes sense with all that information up there. In an effort to make the process more favorable, C is added to the FeO at elevated temperatures. Based on the information above, which of the following gives the value of K and the sign of G for the reaction represented below? So here's my new reaction. Here are my two parts. Let's try to manipulate these and add them together using Hess's law to figure out what our new KEQ is. So my top reaction stays the same, which makes sense if we think about the problem's context, because this is what I want to do. I want to take this and split it apart to make some oxygen. But the second reaction has been flipped around, right? My CO2 is on the opposite side, my CNO are on that side. So when we flip an equilibrium, we have to take the reciprocal. 1 over 1 times 10 to the negative 32 is just 1 times 10 to the positive 32. You take your K1 times your K2 and you multiply them all together. My K1 didn't change. 1 times 10 to the negative 6 times 1 times 10 to the 32. When you multiply, you just add together those exponents. You get 1 times 10 to the 26th as your new K. So that makes the reaction very favorable. K is way bigger than 1, which means this is a favorable reaction, or G is a negative number. D is our final answer. All right, hopefully that's helpful to see all the format of the test. This is probably the of all the tests released, I think the most like what to expect on the AP exam. This one does definitely have some difficulty scaling as you go through it. The actual AP test might be kind of similar. You be smart about that. Spend your time on the first parts of the questions, maybe the first 25, the first 30. The ones at the end, if those are the ones you skip, that's okay. They're all worth the same points in the end anyways. Okay? So hopefully you found this helpful. I do have this full practice test on AP Classroom you can fill out. If you fill out the test and follow along with the video or not, if you try and attempt the test, I will give you some extra points for your grade, some extra credit. All right. I will see you all later. Have a great one.